Okay, hi everybody. So in the interest of time, I thought I would just record this and send it to everybody. I'm going to finish section 3.3 today. And so earlier today, we finished talking about the definition of curvature. And then there was this observation that by the chain rule, we can rewrite it like this. Okay, and so... But also, another observation is we can actually rewrite it like this also. And I would just like to, walk through how the proof of this goes. Okay, really quick for us. And so, all right, great. Oh, whoops, where'd it go? There it is. All right, so... where do we want to start? Let's go ahead and start with this observation here. So kappa of t equals the magnitude of the derivative of t. Now just remember, just because, well, let's see, I don't need to write that out. Just because t hat is a unit vector does not mean that t prime, the derivative of a unit vector, will also be a unit vector. See, so this thing here may not be a unit vector. All right, so that's nice. That's important. Okay, so this magnitude here is not necessarily 1. And then we divide by the magnitude of the derivative of the position vector here. Okay, now notice that, let's go ahead and start with what do I want to do? Let's just look at some observations here. So r prime of t equals the magnitude of r prime of t times the direction of the tangent. Right? That's just the definition of the unit vector of the unit tangent. This is by definition of unit tangent. All right. And so what happens now if we take the derivative of that thing? So r double prime of t is going to equal this derivative which equals now remember though that this right here is the same thing as ds dt. We learned that earlier today, and that's by the definition of ds. So this is the same thing as the derivative of ds dt times t hat t. Derivative. Okay, let's go ahead and take that derivative now. I'm going to use the chain rule. This is a scalar function, so I'm going to have d squared ds dt squared d squared s dt squared, that's the second derivative of s with respect to t, times this thing, plus ds dt times the derivative of my unit tangent. Right there. Okay, so there's that. All right, well, let's go ahead and take this dot product, this cross product now. So if I take the cross product, see, I'm just looking at the top here. If I take the cross product now, I'm going to get ds dt times this crossed with this thing, my r double prime. All right, let me do this dot product. So it distributes. So it's going to be ts dt times d squared s dt times t cross t plus ds dt squared, there are two of them, times dt cross the derivative of t. This is 0. So that whole thing is gone, and so I end up getting ds dt squared times this. Okay. So now remember that since since t is a unit vector, the unit vector of t is perpendicular to its derivative. We saw that earlier. Let me just show you. Where did we see that? We saw that... there it is. This bit right here. So they're perpendicular. The dot product is 0. If the dot product of a function with itself is constant, then the tangent, which is the derivative vector, must be orthogonal to the original vector. And so we're going to use that fact here to compute our cross product right here. So notice, so that means that theta equals 90 degrees, or pi halves. So if I take the magnitude now of this thing, that's going to equal the magnitude of RS RT squared times the magnitude here that equals, let's go ahead and do something about this. This is not actually appropriate to do the magnitude, because this is not a vector. This is not a vector. So this could be drawn with, this ought to be drawn with absolute value squared. And that is really the same thing as r prime of t squared, the magnitude of r prime. So just always remember ds equals this. Okay. So we have that. Now this thing is going to be the magnitude of the unit vector. I think we know what's going to happen there. times the magnitude of the derivative of my unit tangent times the sine of pi halves. Now this is 1, and this is 1. So this equals r prime squared times t hat times the derivative, and that's it. And so, as it happens, the derivative of t hat of t is nothing other than the derivative of my position vector crossed with the second derivative of my position vector divided by sort of a normalization, the derivative squared. And so kappa now of t is going to equal, let me come back up here. Notice we have a formula for that now. R prime t cross r double prime t times this thing cubed. And that's our proof. Okay, now I just want to spend a few seconds talking about normal and binormal vectors. So this is true, right? We know that, and we've seen that before. We just used that fact, actually. So what we'll do is we'll define the unit normal vector. That's going to be the derivative of the tangent normalized. So the unit normal vector of a curve traced out by r. Oh, that's a typo. That should not be a prime. No prime. That's +1 for me. Is defined to be that thing. And so it's a normal vector. It's got a hat on it. And that's the normal. Okay. And so notice this thing here. So this vector is going to be tangent to, oh, I want that to be a hat too. Okay, so there's those. All right. So the unit normal vector, this one, and hat, is going to be perpendicular to the unit tangent. Okay, and so what about their cross product? Is that going to be significant? Well, it turns out that it is significant. We're going to call it the binormal vector. So the unit binormal vector of a curve traced out by, oh, there it is again. There it is again. No prime is defined to be this right here. So let's see if we can make sense of this. So we've got this, well, we'll do that in the example. But how do I know that this cross product is a normal vector? Sorry. How do I know that this cross product is a unit vector? Well, the magnitude of the cross product is the area of the parallelogram. And it just so happens that these are orthogonal. And both of them are unit vectors. So the area here is going to be 1. So it can be shown that the magnitude of this cross product is equal to 1. And so we'll call it a unit vector. All right, some more terminology. The BT-N plane, the B hat, N hat plane, is called the normal plane. So this is at some point. At some point, R of t, we can define a tangent, a unit tangent, a unit normal, and a unit binormal. They're all orthogonal to each other and unit vectors. It's its own coordinate system, an orthogonal coordinate system like the kind we're used to. The plane that contains the b vector and the n vector is called the normal plane. The plane that contains the tangent vector and the normal vector is called the oscillating plane. So I've got my curve here. This is r hat of t. And then here's this t right here. There's a point there, right? And this is r hat t naught. So this is going to be t equals t naught. And that's where that's the end of my vector. Well, so the t goes that way. That's the direction that t goes. N is a little bit trickier to see, but n is maybe, let's say it goes like this. So this is the n hat. And I'm not sure if it goes down or up. Maybe we'll see if that's the case. But it goes something like that, where if this thing were curved, it would curve on the plane of n. I really need to show this to you in 3 dimensions. I'll bring in some wire or something, and we'll talk about the TNB frames. Okay, so there's that, and then B now comes out. B comes out of the paper. Just like that, something like that. It's a unit vector and it's coming out. And that makes my TNB frame. Now I know T is coming out by the right-hand rule, because I know B hat is coming out because of the right-hand rule. I start at T, and then I curl my fingers towards N, and my thumb is pointing up. So that is how it works. So this normal plane has T, the direction of motion has T as the normal vector. And then the oscillating plane is the best single plane that approximates the linearity, or the plane that the curve is on, at the point T naught r. It touches it. It's sort of this tangent plane, but it takes in this curving motion. All right, it touches it. That's why it's called the oscillating plane. Oscillating, sort of Latin for kiss. It just kisses it. Okay, let's take an example. Find the curvature now of the helix from example 1. All right, we can do this 3 ways, and let's do all 3. So, we've got k of t equals the magnitude of this vector here, ds, but it needs to be parameterized with respect to s. Okay, so I do that. So, r of t equals cosine t sine t 1, no, t r of s, as we found, equals cosine s divided by radical 2 sine s divided by radical 2 times s divided by radical 2. R prime then of s, this is the derivative with respect to s, is going to equal 1 over radical 2. You know what? This is just going to be 1 over radical 2 times all this stuff here. Except this right here is going to be minus sine s over radical 2 cosine s over radical 2, and then 1 over radical 2. So the magnitude of this, so that I can get my my tangent vector, is going to be 1 over radical 2, comes out of the norm, comes out of the magnitude operator. And I'm left with this sine squared thing plus the cosine squared thing, which is 1, plus, now this should just be 1, right? Because I factored out a square root of 2. So that's going to be 1, so that's going to give me 1 over square root 2, square root 2, and I end up just getting 1. So as it turns out, the magnitude of the derivative vector parameterized by arc length is 1. And that makes sense when you think about ds equals r prime ds ds. This right here ought to just be 1. Okay, so that's 1. So t hat of s equals r prime of s divided by the magnitude, which equals 1. So that's just r prime of s, which is what we have right here. Now I need to take the derivative of this thing with respect to s and then take its magnitude. So d hat of s of ds equals 1 over square root 2 times, now I take the derivative of all that. I get minus cosine. I'm going to factor out another factor of 1 over square root 2. I get cosine s over square root 2, comma, minus sine s over square root 2, 0. And so that equals 1 over 2 times this, cosine s square root 2 minus sine square root 2, 0. The magnitude of this thing is just going to be 1/2, because this thing here is going to have magnitude of 1. So that means that my curvature is 1/2. Okay, that's one way to do it. Let's do it another way. Kappa of t equals, what was it, ds? Kappa of t equals, there it is, the derivative of the unit vector divided by the derivative of the position vector. So the unit tangent, the derivative, so this is going to be the magnitude of the derivative of the unit tangent divided by the magnitude of the derivative of the position vector. Now this thing here we already computed at least once. That is going to be square root 2. We computed that earlier from our we're using the same one from example 1. That was how we got our arc length function. So we've got square root 2. Now we've got to take the derivative of my unit tangent with respect to t. So r prime with respect to t is going to be minus sine t. So notice it's with respect to t now, so that's a little easier. Cosine t 1. And so I need to take the magnitude of this, which we already know to be 2. And so my unit tangent is going to equal negative, 1 over, it'll equal r prime of t divided by square root 2. And so that's going to be 1 over radical 2 times negative sine t cosine t 1. Now I need to take the derivative of that. And the derivative of that is going to be 1 over square root 2 minus cosine t minus sine t, 0. Now I need to take the magnitude of this. The magnitude of this is going to be 1 over square root 2. So I put that here, 1 over square root 2. And that gives me 1/2, just as it did over here. Okay, now the last one. R prime of t equals negative sine t cosine t 1. R double prime of t equals negative cosine t negative sine t, 0. I cross them now. And get, let's see now, do my I component. That's going to be negative sine, positive sine, 0 times, let's see, negative cosine t, and then sine, and then this one here is just 1. So that cross product is equal to that. Then what I need to do is take the magnitude of that. Well, the magnitude of that is just going to be square root of 2. And then I take the magnitude of my derivative vector, which I already know, that's 2. And then square root 2. And so my formula is kappa of k equals the magnitude of r hat cross r double prime t over r vector t cubed. And that's going to be square root 2 over square root 2 cubed, and that will equal 1/2 again. So we've computed the curvature in 3 different ways. All right, and now we're ready to get to do motion in space. All right, everybody. We'll see you later.